Hello, everybody. My name is Iman Esadi. I am so excited to be filming the first video of what will become my YouTube organic chemistry series. I am excited to do this. I have been a TA/SI leader for this class for several semesters in my undergrad. And as part of the job, I had created a lot of notes and materials for my students. And I thought, why not turn them into videos and make them accessible to a larger population here on YouTube? The way I intend for this course to work is hopefully I'll be publishing 1 to 2 videos per week. If I gain momentum, maybe increasing the number of videos I post if there is a demand. In addition, in the description box, you'll find a link to access these notes, blank and completed, as well as hopefully a transcript/summary of each session, as well as an email address that you can send your questions to. If I get enough questions, I'll make supplementary problem set videos that way. But we'll see how it goes. Anyways, enough said. I am so excited. Let's jump right in. Chapter 1 of organic chemistry, based off of the David Klein textbook. Welcome to Organic Chemistry 1. Whether you are a chemistry major or not, this class is extremely important. You will learn things that are going to benefit and enlighten you. We are, after all, chemical beings, from nutrients to medicine to our bodies, the environment, everything is made out of chemicals. And for these reasons, it's going to serve us well to understand what happens at the microscopic level with electrons, atoms, and all kinds of molecules and compounds. Now, in this course, we are going to study the structure, properties, composition, reaction, and preparation of carbon-containing compounds. And so these first few lectures will cover Chapter 1, which serves as just a general chemistry review. And in this first lecture specifically, we will start by defining what is organic chemistry and comparing it to inorganic chemistry. And then we will jump into a discussion about the structural theory of matter. In this part, we're going to discuss valence electrons and how this concept defines bonding. Interestingly enough, there are different kinds of bonding, and we will also spend some time talking about that as well. And afterwards, we're going to catapult into drawing Lewis structures and understanding formal charges. And we're going to need all of this to fully comprehend Vesper Theory, which will be the last topic of this video. So just an outline of this session. It's going to look something like this. All right. We'll start off with our valence electron discussion. Valence electrons help us understand and visualize how many electrons an atom has in its outer shell, and we can draw that. Actually, knowing the number of valence electrons is going to help us predict the reactivity of a molecule and how it's going to bond. And we can draw this using Lewis structure. And so those are going to be the first 2 topics of our discussion in this video. To verify that we're drawing the Lewis structures correctly, we're going to check that the Octet Rule is satisfied and check for formal charges. And we're going to define what those are in this video as well and make sure we understand that fully, because we need all of this information, valence electrons, Lewis structure, Octet Rule, and formal charges, to finally put it all together and predict molecular geometries using what is called Vesper Theory. And that'll be the final thing we talk about in this video today. All right, so let's get started. Let's jump right in. Inorganic versus organic chemistry. Now, let me set the stage. In the 19th century, in the early 19th century, scientists had some weird definitions for organic and inorganic materials. All right. Organic materials were believed to be derived from living sources like plants and animals, and inorganic compounds were derived from non-living sources like minerals and metals and salts. And this idea was actually called Vitalism. I believe that's how you pronounce it. So this notion that organic materials are derived from living sources and inorganic materials are derived from non-living sources was called Vitalism. And this is completely false definition of these things. And it was proven so by a German chemist named Friedrich Wöhler. And I'm going to write his name right here in the corner. Friedrich Wöhler. I hope I'm pronouncing the name correctly. He disproved these notions and definitions and the idea of vitalism. And he did so by converting an inorganic salt, ammonium cyanate, NH4OCN, ammonium cyanate, into an organic compound called urea. All right. And by doing so, he disproved this idea of vitalism, these definitions, because essentially through these definitions, one would assume that it was impossible to convert between inorganic and organic because you can't go from living to non-living and back and forth. But Friedrich disproved that by converting ammonium cyanate, which is an inorganic material, into an organic material, urea. So now organic compounds became defined as those compounds containing carbon atoms, and inorganic compounds were generally compounds lacking carbon atoms. And so organic chemistry is pretty much the study of hydrocarbons, carbon containing compounds. Now, with these definitions in mind, we want to talk about the structural theory of matter. Each element will generally form a predictable number of bonds, and this is based on valence electron configuration. But what is valence electron configuration? And even more so, what are valence electrons? Well, valence electrons are the electrons that occupy the outermost shell in an atom. They are the determining factor to how an atom will react and how many bonds it can form. Well, from that definition, you can kind of ask two questions. Okay, how can we determine how many valence electrons an atom has? And then from that, how can we determine how many bonds that atom can form? And there are two ways to answer these questions. The first way that we will answer these questions is using electron configuration. And the second way we will answer these questions is using the periodic table of elements. And so using electron configuration, we can answer how many valence electrons an atom has, and then how many bonds that element can form. So let's do a quick example. All right, let's look at carbon, right? Since we're dealing with organic chemistry and carbon-containing materials, let's look at carbon, all right, and see how many valence electrons does carbon have, and then how many bonds can it form. All right, so we're going to look at our periodic table of elements. We're going to find carbon. Here is carbon circled in purple. All right, we're going to write the first step for the electron configuration method is to write the electron configuration for that atom. So we're going to write the electron configuration for carbon. So we're going to do that really quickly here. That's 1s2, 2s2, 2p2. All right, so that is the electron configuration for carbon. We're going to go ahead and write it. 1s2, 2s2, 2p2. Now, the second step is to count the number of electrons that make up the highest shell. All right, so we have some atoms here in the first shell, and we have some electrons in the second shell for carbon. Which is higher? Obviously, the second shell. That is the highest shell that carbon has. So we're going to go ahead and just write that and then count how many electrons make up the highest energy shell. There are 2 electrons in the 2s orbital and 2 electrons in the 2p orbital, and that makes up 4 electrons. That right there is the number of valence electrons that carbon has. Carbon has 4 valence electrons. Now, from this, we can also Predict the number of bonds that carbon can form. All right, we're going to take 4 and we're going to subtract it from 8. And we subtract it from 8 because of the octet rule. The octet rule says that no more than 8 electrons can be around carbon. So we're going to take 8, we're going to subtract it from 4, which is the number of valence electrons. And from that, we get 4. That means carbon can form 4 bonds. In other words, it's tetravalent. Now, this is a very important piece of information that you will use and reuse in organic chemistry, that carbon can form 4 bonds. Now, this was the electron configuration method for figuring out how many valence electrons an atom has and then how many bonds it can form. There is another method, and it's a little bit easier, and it's the periodic table method. All right, if you have an atom of interest, you can identify what group number it falls under. That group number lets you know the number of valence electrons that atom possesses. All right, so again, let's do this. Let's find carbon. Here's carbon. It falls under the 4 group number. That means that carbon has 4 valence electrons. Very easy. All right. And then if you wanted to know how many bonds it can form, again, just 8 minus 4. What about nitrogen? All right, here's nitrogen. Let's do that in blue. Nitrogen is in 5A. That means nitrogen has 5 valence electrons. Well, how many bonds can nitrogen form? Easy. 8 minus 5, that's 3. Nitrogen can form 3 bonds. And you can do that sort of thing with any of the elements that you're going to encounter here in organic chemistry. In organic chemistry, you're pretty much just dealing with these first 2 rows on the periodic table. You won't be looking at pretty much anything else. At least definitely not for organic chemistry 1. Now, some important elements that you're going to encounter quite often are hydrogen, oxygen, nitrogen, and carbon. And it's good to know what kind of bonding preferences these atoms have. Hydrogen has 1 valence electron. Actually, it just has 1 electron, and that's it. And with this 1 electron, it can form just 1 bond. And so hydrogen is known to be monovalent. Now, oxygen has 6 valence electrons, all right? And it can form 2 bonds. So that means that it is a divalent, 2-valent, divalent, 2 bonds it can form. Nitrogen has 5 valence electrons, and it can form 3 bonds. And so it's known as trivalent. And then carbon, of course, as we did the example on carbon, it has 4 valence electrons, and it can form 4 bonds. And so it is called tetravalent. Fantastic. Now, before talking further about bonding, let's discuss how we can use this information about valence electrons to draw Lewis structures. When you draw the Lewis structure of an atom, all you have to do is draw the number of valence electrons around the letter used to denote said atom. All right, the periodic symbol of an atom. So if we want to draw the Lewis structure of carbon, what we're first going to do is we're going to write the periodic symbol of that atom. For carbon, it's just C. All right. And then we're going to draw around it all its valence electrons. All right. Carbon has a total of 6 electrons, but we're not going to be drawing 6 electrons. No, we're only going to be drawing the valence electrons when we do Lewis dot structure. Okay. And so carbon, we just discussed, has 4 valence electrons. So we will only be drawing 4 valence electrons around a carbon. And this is the Lewis structure of carbon. All right. Now, When you see a neutral atom, that means it has no charges. What this means is that the number of protons is balanced by an equal number of electrons. Now, if this is not the case for an atom, then what you're going to have is a formal charge associated with that atom to help us determine whether the atom has more electrons than protons, making it an anion, or if it has more protons than electrons, making it a cation. So if we had to draw a carbon cation or anion, know that a carbon anion, all right, a carbon anion with a negative charge has one more electron than usual. It has one more electron than usual, which is why it's so negative. All right, so this is our carbon anion. It has a negative charge. This tells us, oh, it has one more electron than usual. It has 4 usually, so with a negative charge, it's going to have 1 extra. And so a carbon atom with a negative charge will actually have 5 valence electrons. Now, a carbon cation actually demonstrates electron deficiency, and it's going to have 1 less electron than usual. So here's our carbon cation. You see a carbon with a positive charge. Okay, that means that carbon lost 1 of its valence electrons. So instead of 4 valence electrons, it now will have 3 valence electrons. All right, so the general rule for formal charges is determine the appropriate number of valence electrons for an atom, all right, and then determine whether the electron actually exhibits the appropriate number of electrons, all right, and how off is it if it is off, and then add the appropriate charge that way. Let's do a quick example so we understand what I am saying. All right, we have a nitrogen atom. How many valence electrons does a good neutral nitrogen atom have? Well, it has 5 valence electrons. That means if we see a Lewis dot structure of a nitrogen with 6 valence electrons, whoa, that has 1 extra electron than usual. That means our nitrogen has a negative charge. But what if we see a nitrogen with 4 valence electrons? Hey, that's 1 less than usual. That means the nitrogen has a positive charge. All right, so remember, formal charges are associated with atoms that do not exhibit the appropriate number of valence electrons. All right, so now we've talked about valence electrons. We know how to draw their Lewis dot structures. Let's kind of expand that into a bit of a bigger problem here. What if you're asked to draw the Lewis dot structure for a molecule, not an atom? All right, what if you had to draw the Lewis dot structure for CH2O? All right, how are we going to do this? Well, the first thing that you want to do when you get a problem like this, don't worry. All right, first of all. Second, you want to draw each atom individually with its valence electron. So you have a carbon atom. We're going to draw carbon, and it's 4 valence electrons. All right, 4 because it has no charges. This molecule has no charges, so we're just drawing the neutral valence electrons for each atom. We have a carbon. We draw carbon with 4 valence electrons. We have 2 hydrogens. We're going to draw each one, and remember, hydrogen has 1 valence electron, right? So you see here. Here are the hydrogens. And we have an oxygen. So we're going to go ahead and draw an oxygen, and oxygen has 6 valence electrons. All right, so now we have drawn each atom individually with its valence electrons. The next step is figure out how many bonds each one of these atoms can form. All right, carbon has 4 valence electrons. All right, and it can form 4 bonds. 8 minus 4, right, is 4. Carbon can form 4 bonds. Hydrogens only have that 1 electron, so they can only form that 1 bond. And then oxygen has 6 valence electrons, so 8 minus 6 equals 2, oxygen can form 2 bonds. And remember, we're doing 8 minus the number of valence electrons because we're trying to follow the octet rule. And the octet rule is the tendency of atoms to prefer to have 8 electrons in the valence shell. All right, so to satisfy this 8 electrons in the valence shell, they begin to form bonds with other atoms to satisfy that need. And so we look at a single atom with its valence electron. Oh, how many bonds can it form to finally satisfy that 8 electrons in the valence shell? That's how we're determining this, guys. All right, so we've drawn each atom individually, and we've written down how many bonds each one of these individual atoms can form. Now, atoms that can form the most number of bonds are going to be our central atoms, are most likely going to be our central atoms. All right, so out of carbon, 2 hydrogens, and an oxygen, which one of these atoms can form the most number of bonds? Well, it's very clearly our carbon. Our carbon can form the most number of bonds. And so it's going to be our central atom. So we're going to put it here in the center. Now we want to attach atoms to this carbon so that all the bonding preferences are satisfied without creating any formal charges, okay? So here's how this is gonna go. We have our carbon, it's our central atom. Let's see how we can potentially attach everything to this carbon. All right, can we attach a hydrogen? Okay, it can only, this hydrogen can only form 1 bond. Cool, we can attach the other hydrogen. So far, so good, so far, so good. All right, and maybe we can attach the oxygen to the carbon. Cool. So our hydrogens each are forming 1 bond. Check and check. Their bonding preferences are satisfied. Now, what about that central carbon? So far, it has 1, 2, 3 bonds. It needs 1 more for its bonding preference to be satisfied. And then if we look at the oxygen only has 1 bond. It needs another one to be satisfied. Okay, cool. So if that's the case, we probably should double up this bond and have a double bond between the oxygen and the carbon so that their bonding preferences are satisfied. And so this is going to look something like this, right? This carbon is going to form a bond with the hydrogen. So now they're sharing their electrons. And it's going to form another bond with the other hydrogen. And they're sharing their electrons. Cool. So the carbon has 4 electrons around it right now. And if it forms this double bond with the oxygen, all right, now it has all 4 bonds satisfied. Fantastic. And the oxygen has its 2 bonds and it's satisfied. And all the atoms' bonding preferences now are satisfied. And that is what you want to make sure of when you are drawing the Lewis structures for molecules. And sometimes it's going to take a little bit of trial and error, and you'll attach things and then you'll double check, oh, is the octet rule met? Am I making sure I'm following whatever formal charges or lack thereof when I'm drawing the molecules, and making sure that everything looks appropriate? And that's okay. Sometimes you're going to have to sketch out something that might initially be wrong and then fix it as you go. And sometimes draw out all the electrons out if you need to visualize it better. Now let's use this example to segue into bonding and the different kinds of bonding. All right, so I'm going to zoom out just for a little bit, just so you can see the whole flow chart for bonding. All right. There are 2 main types of bonding we will focus on here, and those are covalent bonding and ionic bonding. Ionic bonding is when the valence electrons from one atom is lost to a more electronegative atom. This results in oppositely charged ions. All right, and an example of this is, for example, sodium chloride. Sodium chloride, the way that sodium and chloride bond is through ionic bonding. Sodium has 1 electron in its valence shell, and chlorine has 7. Whenever sodium and chloride form a bond, chloride pretty much steals the electron of sodium. It's like, gimme, gimme, gimme. It's pretty selfish because chlorine is more electronegative. It's more electronegative because it has more electron density around it. And so it goes ahead and just steals the electron from sodium. All right. And then what you get as a consequence of that is now sodium has lost an electron. So it has a positive formal charge, and chlorine has gained an electron. And so it has a negative charge associated with it. All right. So ionic bonding occurs when one atom steals the electron from another. And as a consequence, you get these oppositely charged ions. Now there's a more rigid definition for ionic bonding, and we're going to get to that in a little bit. Let's quickly talk about covalent bonding in the general sense as well before we get to the specific definitions for what makes a covalent bond and what makes an ionic bond. Covalent bonding results when 2 atoms share a pair of electrons, and there's two kinds of covalent bonding. There is polar and non-polar. Now, polar covalent bonding is when one atom will love electrons a little more than the other, and it's going to slightly pull the electrons towards itself. What this means is that even though they're forming a covalent bond where the 2 atoms share a pair of electrons, one atom will slightly love the electrons a little more and pull them a little closer to it. And this is going to create a partial charge on the atoms. Non-polar covalent bonds are when 2 atoms share a pair of electrons equally. No single atom is like being a little greedy and pulling the electrons more towards it. The electrons in the bond are shared equally. Now, what variable do we use to determine what kind of bonding is occurring? Right? How do we know when ionic bonding is occurring, when covalent bonding is occurring, when specifically non-polar or polar covalent bonding is occurring? What variable are we using to define the limits of each of these bonding types? And the answer to that is electronegativity. This is the measure of the ability of an atom to attract an electron. And each atom has an electronegative value. And we can see this in this table right here. These are the electronegativity values of some of the common elements that you're going to see in Organic Chemistry 1. Now, we're going to use these values to help us define what makes an ionic bonding, what makes a polar covalent bond, and what makes a non-polar covalent bond. So let's look at this. A non-polar covalent bond is defined as when the electronegativity difference between the 2 atoms that are forming a bond is less than 0.5. Whenever the electronegativity difference between 2 atoms that are forming a bond is less than this value, then what is occurring is a non-polar covalent bond. Let's look at an example. Let's look at carbon and hydrogen. Carbon has an electronegative value of 2.5, and hydrogen has an electronegative value of 2.1. Let us subtract these two numbers. 2.5 minus 2.1 is going to equal 0.4. That is a electronegativity difference that is less than 0.5. That means that the bond between carbon and hydrogen is a non-polar covalent bond. Now, how do we define polar covalent bonding? Polar covalent bonding is defined when the difference in electronegativity between two atoms forming a bond is anywhere between 0.5 and 1.7. Let's look at carbon and fluorine as an example. Carbon has a electronegativity value of 2.5, and fluorine has an electronegativity value of 4. So we're going to take the difference between those two. We're going to do 4 minus 2.5, and that gives us 1.5. 1.5 is between 0.5 and 1.7. That means that the bond between carbon and fluorine is a polar covalent bond. Now, lastly, how do we define ionic bonding using electronegativity differences? Well, if the difference between two atoms forming a bond is greater than 1.7, then you have an ionic bond. So let's look at our example of sodium chloride. Chloride has an electronegativity value of 3 and sodium of 0.9. So let's take that difference. 3 minus 0.9 equals 2.1. That is greater than 1.7. Therefore, sodium chloride is an ionic bond. The bond between sodium and chloride is an ionic bond. And so we use electronegativity values and the difference between them to determine whether the bond between two atoms is ionic, nonpolar covalent, or polar covalent. And this will be really important later on. Most of the time also, this kind of table is usually given to students for tests. So you usually don't have to memorize this kind of stuff, but it's also really good to do enough problems to familiarize yourself and be able to remember a few of these numbers just off the top of your head. Now, with everything we have learned, with everything that we've learned to help us understand and properly draw molecules using Lewis structure, we can talk about Vesper theory. Vesper stands for Valence Shell Electron Repulsion theory, and it's a model used in chemistry to predict the geometry of individual molecules from the number of electron pairs surrounding the central atom. So if we are interested in predicting the molecular geometry of an atom in the molecule, Vesper allows you to do that just by observing the number of electron-dense areas around the atom and the number of lone pairs. We will, of course, do some examples now to kind of reaffirm what I just said. Now, the best thing to use when trying to understand this is a table like this, all right, where you have number of dense electron areas going down here, and then number of lone pairs right here. And so whenever you figure out around a central atom, the number of electron dense areas and the number of lone pairs, you can go ahead and then figure out what kind of molecular geometry a specific atom has. So let's quickly do an example. What if we had BH3? All right, I'm just gonna quickly draw out B and the 3 hydrogens surrounding it. All right, so first question we want to answer. Oh no, I can't erase these arrows. That's okay. We will work around that. That is my fault. How many electron dense areas are around boron? All right, there's 1 right here, 2, and 3. So there are 3 electron dense areas around boron. Now, how many lone pairs are around boron? There are none, 0. Every single electron in the valence electron of boron, which is 3, is forming a bond with the hydrogen. So there are no extra lone pairs sitting around boron. And so 0, there are no lone pairs. So what we're going to go ahead is draw to where that takes us. And we end up right here. So the molecular geometry of BH3 is a trigonal planar. And so we're going to be using this table a lot to predict the molecular geometry of molecules. Fantastic. Now, what we want to do is just do a couple of quick practice problems to reaffirm all the things that we've learned so far in this session. All right. So these are the topics here just written out quickly for you of what we just covered. We talked about organic versus inorganic chemistry. In organic chemistry here, we're going to focus on carbon-containing compounds. We talked about valence electrons in the 2 different ways that you can determine how many valence electrons are around an atom, and then how many bonds can that atom form. And we took all that information and we also learned how to draw the Lewis structure of an atom and then for molecules. And we learned the different kinds of bonding that can form between atoms. Ionic and covalent polar and covalent nonpolar. And we learned that the variable that we use to distinguish between what kind of bonding is occurring between 2 atoms is electronegativity, and the differences between electronegativity of the 2 atoms that are participating in a bond. And lastly, we tied it all in by talking about how Vesper is used to predict molecular geometry. And all you need to know in order to do that is use a table, and you look at a molecule, you determine how many electron dense areas is around the central atom and how many lone pairs that central atom has. And then you just follow the table to determine what kind of molecular geometry an atom, a molecule or compound possesses. So let's take that and do a couple practice problems. First practice problem, draw the Lewis structure of CH3OH. All right, we're going to follow all the same steps we talked about earlier. First step, draw the valence electron for each atom individually. Here we have our carbon, our 3 hydrogens, our oxygen, and then that 4th hydrogen. Next, we want to answer how many bonds can each atom form. Well, carbon can form 4, all the hydrogens form only 1 bond, and oxygen forms 2. Now, what is the best way to bond these? All right, remember, we want to make sure that the octet rule is satisfied. And since this molecule has no formal charges, we want to make sure we keep everything neutral and we don't create any charges through the way we try to bond these, okay? And so let's try it out. Let's draw our carbon. Our carbon forms the most number of bonds, so it is going to be our central atom. All right. And now we want to figure out how to attach all these atoms to the carbon. And remember, this might take trial and error, and that is okay. Now, maybe you're going to get really excited and draw all 4 hydrogens around the carbon. Yay, carbon has 4 bonds and all the hydrogens have 1, but then you forgot an oxygen. So obviously not correct. Let's erase one of those hydrogens. We got a little too excited. Okay, what if we draw oxygen to that carbon? Cool, that carbon has all 4 bonds. All the hydrogens have 1 bond, just like they should, but that oxygen needs 1 more bond. Oh, maybe we can attach the last hydrogen to that. Oh, well, look at that. That works. It follows the octet rule for each atom. And so at the end, we figured it out. It's okay if it takes you several trials to figure out how to bond the atoms. Just always fall back to your octet rule to double check. Okay, let's do one more. Borane, BH3, we kind of already drew this prior, but we're going to do this step by step. Is very unstable and quite reactive. Draw the Lewis structure and explain the source of instability. So remember, draw the valence electrons for each atom. Boron's right here. That's a bad circle. Boron's right here. It's in group 3A. That means it has 3 valence electrons. And each one of our hydrogens has one valence electron. Now, how many bonds can each atom form? Boron, 8 minus 3, boron can form 5 bonds. And each one of these hydrogens can form 1. All right, so let's try to attach these, keeping in mind we want to satisfy the octet rule. Well, here's the boron, and each single one of those electrons it has is going to bond to a hydrogen. Now, that's the correct way to draw this. But the reason why it's so unstable is because that central boron lacks an octet of electrons. And so even though it forms 3 bonds with hydrogens, all 3 electrons that boron has in its valence electron shell is bonded to an atom, it still lacks an octet. And that's why it's really unstable and reactive. All right, let's do another problem. Identify any polar covalent bonds. All right, cool. Let's do that. Let's go through each one of these bonds and find the electronegativity differences between them and categorize them. All right, we'll start here. Carbon and chlorine. Carbon is 2.5, chlorine is 3. 3 minus 2.5 equals 0.5. Now, if you remember, when the different electronegativity difference is less than 0.5, that's non-polar. Whenever the electronegativity difference is between 0.5 and 1.7, that's polar. Well, 0.5 tends to fall on the border of these two things. So is a carbon-chlorine bond polar or non-polar? The answer to this is that it is polar. And the reason for this is because if you were to take more accurate electronegativity values, ones that had more decimal places than what you see in this basic chart, the difference is actually slightly greater than 0.5. It is, I think, around 0.511 or something of the sorts. And so that makes carbon-chlorine bond polar. Now, this is the chart that's in the David Klein textbook and one that you use for most of the problems in the textbook and for the classes that use that textbook. And so, of course, you don't have electronegativity values that go up to the thousandths or millionths decimal place. And so the electronegativity difference values that you get sometimes fall in the border, and you kind of have to figure out whether it's leaning towards polar or non-polar, for example, like we did here. And the reason why I want to do this example is to state that a carbon-chlorine bond is in fact a polar covalent bond. Now let's do carbon and fluorine. Fluorine is 4 and carbon is 2.5. The difference between them is 1.5, very clearly a polar covalent bond as well. So we've identified 2 polar covalent bonds so far. What about our carbon hydrogens? Well, hydrogen is 2.1 and carbon is 2.5. The difference between them is 0.4. Awesome. So that's obviously non-polar. So we're not interested in that. We're only wanting to identify our polar covalent bonds, which is the carbon fluorine and the carbon chlorine. Fantastic. Now, let's do a couple of Vesper theory problems. Using Vesper theory, predict the geometry for the following structure. All right, we have ammonium, NH4. All right, and I've went ahead and drawn the Lewis structure for you for this molecule. Now, the first question that you want to ask is, well, you can ask either of one of these questions in any order. I actually like to ask this question first. How many groups around the central atom? Or in other words, how many electron dense areas are there around this atom? Well, here's 1, 2, 3, 4. Now, I want to quickly make note of something. The reason why I say how many groups or electron dense areas instead of bonds is because if you have, say, something that looks like this, All right, this is just random, okay? If you're trying to find the Vesper theory for a molecule like this, all right, you're going to ask yourself how many groups or how many electron dense areas are around this molecule. This is 1, this is 2, and this is just 3. You do not double count for double bonds, which is the reason that we use the word group or electron dense areas, as to not say bonds and then you double count double bonds or triple count triple bonds. All right, we're not counting the number of bonds per se, we're counting the number of groups or electron dense areas around the central atom. So that's the distinction between that and the reason why I'm trying to be very careful in using the word groups or electron dense areas. So how many electron dense areas are around nitrogen? Well, we counted and it is 4. Then we want to ask, does the central atom, this nitrogen, have any lone pairs? Well, remember, nitrogen usually has 5 valence electrons around it, but this nitrogen has a positive charge, so it lost an electron. So this N plus has 4. So an N plus has 4 valence electrons around it, and it already has all 4 valence electrons here. And that means this nitrogen has no lone pairs. So 0 lone pairs. 4 groups and 0 lone pairs. Let's use our table for electron dense areas with no lone pairs. The shape of ammonium is a tetrahedral. And so it looks like something like this if you were to appropriately draw it in 2D. Let's do one more for good measure. All right, let's look at this atom. All right, how many groups or electron dense areas does this molecule have? 1, 2, 3. All right, so 3 electron dense areas around this molecule. And then we want to ask, does the central atom have any lone pairs? Well, there are no charges on the carbon, and so the carbon has its usual 4 valence electrons, and it's forming 4 bonds, so all 4 electrons are there. So no lone pairs on this carbon. So 3 groups and 0 lone pairs. Let's go ahead and look at our table. 3 and 0 lone pairs. This molecule is a trigonal planar. And if you were to appropriately draw it in 2D, that's what it would look like. Now that is the last thing for this video. We talked about valence electrons, Lewis structures, our octet rules and formal charges, as well as Vesper theory. So we've covered everything we want for this video, as well as we've done a few practice problems. I hope this helps. Next video, we're going to cover the latter half of chapter 1. We're going to focus on atomic orbitals and hybridization. If you have any questions about this session, or if you have any problems that you would like me to do in a problem set, go ahead, leave your questions in the comments below, or email me problems that you would want to see, and I will try my best to reply or make a video to answer everybody's questions. I really hope this was helpful, and I will see you in the next video.